All right, welcome, ladies and gentlemen, and all you lovely statistics folks. Here we have another statistics video for you. Today we're going to be finishing up talking about experiments. We're just going to sort of recap all the experiment stuff that you've seen, sort of do some summing up, and we'll see how it feels, and then we'll go through a very specific sports related example. All right. So, first off, some terminology. An experiment is something that is unlike the observations that we've been doing, where we can only really identify some correlation or some association between variables. Our experiments, we control as many variables as we can, with the exception of one, and we impose that one treatment on individuals. And again, treatment in individuals is kind of uh, sciencey talk for things participating in the experiment. All right. So our treatment, our experiment, we're imposing treatments on individuals to measure their responses. Okay. The treatments are what each individual in an experiment is designed to do, is assigned to do. Okay. So whoever is participating has to be assigned some sort of treatment. And that can be as simple as you don't get the thing that we're testing, or you do get the thing that we're testing. Okay, or it could be something a little bit more specific than that, and we'll talk about that later. A response variable, that's the outcome, that's the variable that we're interested in. Did thing X go up? Did thing Y go down? Was there any impact at all? What sort of thing were we looking at? So that's our response variable. A response variable is the outcome. Our explanatory variable is the variable that we're testing for, the thing that we're changing, the thing that we are deliberately modifying to see if it causes a change in that response variable. Okay, that's the thing that we're testing. Whenever we assign individuals to groups in order to in order to apply treatments to them, we want to make sure that that is done randomly. We want to have a large enough size, and we want to make sure that that sample is that we select is random. All right, random, random, random. Random is the name of the game when it comes to experiments, and we want to eliminate everything that is not random. So, with that, we then control all the other things that can affect our response variable. We want to keep conditions exactly the same for every single trial, with the exception of the explanatory treatment. Okay, we want to control all of those. Okay, so with those ideas in mind, let's take a look at an experiment in depth where we're going to take home runs and compare it to bat weight. All right, so many people believe that if you have a heavier bat, you hit more home runs. Um, so there was a softball player who decided to try out two different bats. All right. Normally she uses one that weighs 28 ounces, and then she also wants to see if increasing that bat weight by 2 ounces will noticeably improve her ability to hit home runs. So our plan is to use each bat 100 times and record whether or not she hits a home run on each swing of those bats. Okay? So that's what we're looking at. So, with that in mind, what are our variables? What's our explanatory variable? What's the thing that we are trying to decipher and see if it makes a difference? And then, what's our response variable? What do you think the what do you think our outcome is? Our outcomes that we're looking for. All right. So, hopefully you came up with the explanatory variable. The thing that we're changing is the bat weight, the weight of the bat, either 28 or 30 ounces. Right? 28 or 30 ounces for that bat weight. We have two. And then hopefully you came up for your response variable is whether or not we're getting a home run. If we hit a home run, that is our success. If we don't hit a home run, that's considered not a success. All right. So again, here is the situation. Take it, read it again. So we have our treatments that we're going to be applying and our variables that we're going to be looking at. All right. So what are those treatments? What are the treatments that we're going to be applying? All right. Either she's going to hit with a 28-ounce bat, or she's going to hit with a 30-ounce bat, and that should be it. One of those two, and that's it. All right. Everything else should be the same. Should be controlled. All right. Here's our scenario again. Feel free to pause, reread. Because how are we going to randomize the order that the bats are used? We want to make sure that she's not using one bat all the time and then switching over to another bat and using that bat all the time. How can we randomize that? See if you can come up with a way that you might want to randomize that. Feel free to pause the video. Okay? Why would it even be important to randomize the order that the bats are being used? Why would that be important? Why wouldn't we want to, use one bat all the time and then switch over to the other bat and see what happens? All right? Why would that be important? All right? So let's take a look. Here's a way that I would say we could randomize the order of the bats. We could take 100 tiles, put the number 28 on it, and then take another 100 tiles, put a 30 on them, and toss them in a bag. Shake that bag around, and then pull one out and say, okay, next we're using this tile. We don't put that tile back in the bag, and we keep pulling tiles out until we're all out of tiles. Okay, and so this is important because we don't want to have anything that could impact our variable that's not the thing that we're testing. All right, we don't want any confounding variables to show up. For example, say we had her hit with the 30-ounce bat 100 times, and then we had her hit with the 28-ounce bat. Okay, if that was the case, maybe she was starting to get tired by the end. Swinging a bat 100 times or swinging a bat 200 times is not easy. All right, maybe the sun position changed significantly between the beginning of the 30-ounce bat, the 30-ounce when she was swinging with a 30-ounce bat, and when she's now swinging with a 20-ounce bat or the 28-ounce bat. Maybe the weather changed. Maybe the wind changed. If we keep randomizing this, if we keep making sure that all these are random swings with these bats, then it doesn't really matter if the sun changed position, because she has swung a couple times with the 28-ounce bat and swung a couple times with a 30-ounce bat. If she is starting to get tired, well, then it won't matter which bat she has at the end, because she's just tired and hitting both of them with the same viciousness. I don't know. She's hitting them both the same as far as how hard she's hitting them. All right. So we want to make sure that we are randomizing the individuals in this trial. Which the individuals in this trial, since there's only one person swinging the bat, the individuals are each swing. Okay, are each swing. We want to make sure that those swings either get put into the 28 category, the 28-ounce category, or the 30-ounce category, completely and totally randomly. All right. So again, there is the scenario. I'm going to keep showing you that after every question, just so you have a chance to reread and remind yourself of all the things that are going to be going on. Okay. So controls. What are some key variables we would want to control for and make sure that they have a similar effect of the outcome regardless of the status of that expository variable, regardless of whether she's hitting with a 28 or a 30-ounce bat. Okay? See if you can come up with a few. I came up with 5. A few more than that, but 5 main ones. Go ahead and pause the variable. Pause the variable. Pause the video. See what you come up with. All right, so one of the things I came up with was making sure that she uses the same ball for each of them. We don't want her to use a white ball for some of them and one of the like Dayglow yellow balls. We don't want her to use one of those for one and one for the other. We don't want her to use brand new balls at the beginning and use really old beaten up ones toward the end. We want her to be using the same ones every single time. Okay, so that's one thing that can change. Feel free after each of these to pause and add to your list if you can think of something that maybe you didn't have on your list before. Pitches. We want to make sure that all those pitches are exactly the same. We want to make sure all those pitches are as close to identical as we can make them. In fact, it would probably be even best to use a pitching machine rather than an actual pitcher, just to have that added level of consistency. So that way the ball is always coming in at the same speed, same height, same everything. It's all the same. We can control for that. Variable. Bat length. We want her to use the same length bat, even though they're different weights. The same length bat can make a difference in where that sweet spot on that bat is. So we don't want her to be using different length bats, even though they might be different weights. We want it to be the same brand of bat. different companies manufacture bats with different technologies built into them, so we want her to use the same brand of bat for for every single for every single swing. Um, but one is just 28 ounces and the other is 30 ounces. All right. Another one that we might want to switch, that we might want to control for, is the model of the bat. All right. Again, even within the same brand, they make a bunch of different models of bats. So with different technologies, different sort of weight distributions, all that sort of stuff. So we want to make sure that she's using one bat model for the entire swing set of swings. All right. There's a whole bunch of other ones that we want to control for, but these were just 5 that I came up with. All right. So for this scenario, what would your hypotheses for this experiment be? First off, what's your null hypothesis? What's your null hypothesis? Sorry, I misspelled it. What is your null hypothesis? Remember, this is the one that we don't want any change to be happening. So we would say what about her swinging the 28 ounce and the 38 ounce bat, regardless, talking about how many home runs she hits. Well, and then what would you say the alternative hypothesis would be? This is where we expect that change to happen. This is where we say, okay, here's the change. Here's the thing that we're expecting to happen with this, right? So for a null hypothesis, something along the lines of her ability to hit doesn't change. Her ability to hit home runs doesn't change regardless of what bat she's using. All right, so she has the same ability to hit home runs regardless of the bat would be an example of a null hypothesis you could use for this. And an example of an alternative hypothesis you could use would be her ability to hit home runs increases with the heavier bat, right? These are options of things that you have to say. They don't have to be worded exactly like this, but they should be along these lines. The null hypothesis should say things are going to stay the same. She's going to have about the same ability to hit home runs with either bat. And then the alternative hypothesis should say that that ability is going to go up with the heavier bat. Okay, so if we did this experiment, and let's say I did this experiment, when we got this data, all right, let's say we did this and we counted and everything was nice and random, everything was exactly the way that we want an experiment to happen, and we got that she hit 36 home runs with the 28 ounce bat and 57 home runs with the 30. Oh, sorry, that should be a 30 ounce bat. Fix that, make that a 0. All right, typos are a thing. All right, so. And we said that she swung 100 times with both of them. All right. So just like in that last video that we had, I used that applet online, that statistics applet, and said, okay, I put this data in 36 out of 100 and 57 out of 100. I think I might have flipped the order of them, but doesn't matter really. But it came up with this graph. All right. So that difference in proportions. So how likely is it? How often, if we run 1,000 simulations, how often is she going to have a difference in proportions that is along the same lines as what we're seeing here? All right. So if there's no difference, here's how often we would see this. But for this particular difference in proportions, the only time that we would have 0.21 greater with the 30 ounce bat than the 28 ounce bat, we would have that 3 times out of 1,000. Okay, 3 times out of 1,000. All right. So, actually, I found out that I made a mistake, but just roll with it. Okay. All right. So, if we have 0.0, it should be 0.003. So this should be 0.03%, but this should be 0.03%, and this should be 0.003 because I did 1,000. I thought I did 100. We want to figure out what that would mean. So remember, with a p-value of 1, we have our sort of our general rule of thumbs. If p-value is less than 1% or less than 0.001, or excuse me, 0.01, we say that that is very convincing evidence to reject the null hypothesis. So very convincing evidence that whatever our alternative hypothesis is, in this case, our alternative hypothesis was her ability to home run increases with the heavier bat. We say that this null hypothesis, the same ability to hit, go away. How are people supposed to read if you're there? Okay, well, fine. We'll make the dot go away, and then hopefully that'll go away. So our null hypothesis says she has the same ability to hit home runs regardless of the bat. because if we say that our p-value is less than 1%, that's very convincing evidence to reject that null hypothesis and support the alternative hypothesis. Likewise, if our p-value is less than 5% or less than 0.05, that is said to be convincing evidence to reject the null hypothesis and support the alternative hypothesis. And if our p-value is greater than 5%, at that point we say, you know what, randomness could have played a part in how this happened. It's not unlikely that randomness could be a thing, so we have insufficient evidence to reject the null hypothesis, and we can't support that alternative hypothesis. We can't say, in this case, that the bat makes a difference. But since our p-value for 1,000 trials was 0.3% or 0.003, we're up here in this space. So since we had very convincing evidence, we would reject the null hypothesis in favor of the alternative. Okay? We would reject the null hypothesis in favor of the alternative. So for us, we're saying that, yeah, this alternative hypothesis, her ability to hit home runs increases with a heavier bat. Okay? That hypothesis, we say, is a thing. Okay? So now, what does that mean? Can we say that the heavier bat was the cause of her increased ability to hit home runs, or is it just sort of a coincidence? Is it just a correlation or some sort of association that we can make between heavier bats and home runs? Well, in this case, because it's an experiment where we controlled for a bunch of variables, we can say that yes, it was the cause of her increased ability to hit home runs. Her actual ability went up, and it was caused by that heavier bat. Because we did an experiment. That should say and, not and. Be careful when you're typing, children. Because we did an experiment and controlled all those other variables, and we did everything randomly. We did everything, all the sort of rules and regulations when it comes to experiments. We did all those. We can establish that cause and effect relationship. Okay, heavier bats in this case make for more home runs. Okay, and that's for this specific batter, right? It was one person who was doing all the batting, so for that batter, that heavier bat causes her to hit more home runs. Okay, so that's an example of an experiment, and talking all the way through it. We're going to keep talking about this tomorrow at our live session. So please, please, please feel free. Or actually, it's probably today by the time you're watching this. So, so please, 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 if you have any questions, let me know. I'll be happy to talk about it. Happy to help you think through some of this sort of stuff, and we'll talk through another one of these experiments tomorrow. All right. Have a great day, and I will talk to you later. Bye.